Hello everyone, and welcome to the video for section 8.3, where we're going to be solving systems of linear equations using matrices. The skill objectives for this particular video are: number 1, write a system of linear equations as an augmented matrix. Number 2, perform row operations on an augmented matrix. Number 3, use Gaussian elimination with back substitution to solve a system. And number 4, use Gauss-Jordan elimination to solve a system. The two processes that you have here, the Gaussian elimination, Gauss-Jordan elimination, are very similar. The Gauss-Jordan elimination just adds on what amounts to one additional step. Our conceptual objectives for this particular video are: number 1, visualize an augmented matrix as a system of linear equations. Number 2, understand that solving a system with matrices is equivalent to solving by elimination. And number 3, recognize matrices that correspond to inconsistent and dependent systems. Now, the first thing we need to do is really go through and define what a matrix is. A matrix is a rectangular array of numbers. So what you're going to see these brackets there, and then you're going to see different entries or elements in the matrix. All these you'll see A sub 1, 1, A sub 1, 2, A sub 2, 3, and so forth. All of those are elements of the matrix. And the subscript notation, as you can see here, A sub 2, 3, tells us which row and what column it's in. So the first number tells us the row, second number tells us the column. So A23 would be in the second row, third column. The order of the matrix is always equal to the number of rows by the number of columns. So in this particular problem, because I have m rows, the first number tells me rows, and n columns, this particular matrix would be said to be, in general, an m by n matrix. So the order of that matrix up there is m by n. Another piece of terminology you want to be aware of, and it happens when you're dealing with when you're dealing with the number of rows and columns being equal. In other words, if m and n are equal, then we call the matrix a square matrix. And the elements in the first row, first column, second row, second column, third row, third column, and so forth, those elements form what's called the main diagonal. So you'll hear both those terms, square matrix and main diagonal, as we move forward. Now, the next thing we want to do, though, is we want to take a look at identifying the order of the different matrices. So you see 5 different matrices here. We talked about order last time. What I want you to do is pause the video, and I want you to write down what you think the order of each one of these matrices will be. Once you have that, come on back, and we'll go through those. Welcome back. So at this point, I'm assuming you have gone through and identified your orders, what you think are the orders of each one of these matrices. In this first one, in number 1, in this case, you'll notice we have 2 rows and 3 columns. So the order of that matrix would be a 2 by 3 matrix. In number 2, we have 1 row and 4 columns. So that would be a 1 by 4. Number 3, that one is 3 rows and 3 columns, so there's a square matrix. And the elements 4, 5, and -1 would be the elements on the main diagonal. Then number 4, we have 3 rows and 1 column, so that's a 3 by 1 matrix. And in number 5, we have 4 rows and 3 columns, so that would be a 4 by 3 matrix. Double check, make sure you have those. Hopefully you do. If not, make sure you understand that the first number in the order tells me the number of rows, and the second one tells me the number of columns. The next thing we want to do is use what's called an augmented matrix to represent our system. Now, what happens with an augmented matrix? You're going to have, you're going to see a number of rows is going to be equal to the number of equations you have. And the number of columns will be always 1 more than the number of variables. And you're going to see a dotted line. The dotted line represents the equal sign. Now what you want to do to go through and write a system in terms of an augmented matrix, you want to make sure that the equations have all the variables on one side and any constants on the other. So in our first example, you'll notice that 2x plus y minus 3 equals 0 has the minus 3 on the left. We want to go and move that to the right. So when I do that, I'm going to get 2x plus y equals 3. And on the bottom, I'll have x minus y equals 5. So the augmented matrix here for this one, I am going to go through the equal sign. What you see as that equal sign is going to be represented by the dashed line there. And so I will take the coefficients that I have for the first equation. I have a 2 on the x and a 1 on the y, and then it equals 3. And on the second equation, I have a 1 on the x, negative 1 on the y, and it equals 5. So that would be my augmented matrix for that particular system. In the second example, one of the issues you have, you need to have all the variables, you want to have it be consistent. So generally speaking, in this case, we have an issue because of the fact that the x, y's, and the y and z in the third one are not in the proper order. So what I'm going to do on that is I'm going to rewrite that. The first equation will become minus x plus y plus z equals 7. The second one will be x minus y minus z equals 2. And the third will become, there's no x, so just minus y plus z equals negative 1. And so I want to write that now as an augmented matrix. My first equation is the coefficients are negative 1 on the x, 1 on the y, 1 on the z, and then I have my equal sign, and it equals 7. My second equation, the coefficients are 1 on the x, negative 1 on the y, negative 1 on the z, and it equals 2. Now in the third equation, I don't have any x. So that means that I have 0 there as a coefficient on the x, negative 1 on the y, 1 on the z, and it equals negative 1. So that's a 7. So this right here would be the augmented matrix for this particular system. Now what you have here, when you look to the left of that dashed line, so this portion right here, that's called the coefficient matrix, and this would be like the solution matrix. Here's the coefficient matrix, and there's the solution matrix. Now to work with matrices, we have, to solve them, we need what are called row operations, and there are 3 row operations that we're going to be working with. Number 1 is where I can go and interchange 2 rows. I can just switch the rows and it will give me an equivalent matrix. It doesn't cause any problems. Number 2 is I can multiply a row by a non-zero constant. Okay, so if it's going to help me to multiply the third row by a negative 7, then I can do that. The third thing I can do is add a multiple of one row to another row. Okay, now the notation for that, if I want to go through, when you look at the matrices and when we do these operations, you're going to want to use this notation to go through and make sure it's clear what you meant to do. So in the first one here, when I see r sub I with this arrow, double arrow like that, r sub j, that's telling me I'm interchanging row I with row j. So I'm going to replace row I with row j, and I'm going to replace row j with row I. I'm going to switch those 2 rows. The second one here, you'll see if I take some c times r sub I goes into r sub I. So that means what I'm going to do is I'm going to multiply row I by some constant, by some scalar c, and I'm going to put that right back into row I. I'm going to replace row I with whatever that constant times its coefficients is. And the last one, probably the most common one, this is the one you're going to use most often. I'm going to take a constant times row I, add it to row j, and I'm going to store the result into row j. So multiply some constant times row I, add that result to row j, and I'm going to put that in for row J. Let's take a look at a couple of these, how these things work. In this first example, what you're seeing is we're going to interchange row 1 and row 3. So what's going to happen here when I do this? I'm going to go and I'm going to take what is in row 3, move it up to row 1. So it's going to be -1, 0, 3, and then the 1. The second row is going to stay the same, 2, 4, 5, and 7. And then what was the third row, or what was the first row, is now going to be in the third row. So I'll have a 1, 2, -1, 3. So that's what it looks like when we interchange two rows. We just took the entire row 1, moved it down to row 3, and we took row 3, moved it up to row 1. Now in the next example, what we're going to do is we're going to take 3 times, we're going to multiply row 2 by 3. So in this example, what happens, row 1 stays the same. It doesn't change. So I'll have a 2, 1, 7, augmented with a 3 there. And then when I take 3 times row 2, 3 times 1 is 3. So that'll be a 3. 3 times 5 is 15. So we have that. 3 times 0 is 0. And 3 times 2 is 6. So that's what happens when I just multiply a row by a constant. I'm just multiplying each entry in that row by that constant, and that's what the result is. Now what we see in the next one, I'm going to take 2 times row 2 and add it to row 3 and put that result in row 3. So what this is telling me first up is that row 1 and row 2 are not going to change. So I'm going to have row 1 will be 1, 2, 1, and then a 1. And row 2 will be 0, 1, -2, and 3. And now what I'm going to do is I'm going to multiply row 2 by, I'm going to take 2 times row 2, add it to row 3. So when I take 2 times 1, that's 2, add it to 2, that's going to give me a, well, let's start back up here. First thing I have is 0 times 2 added to 0. That's going to be a 0. Then when I take that 2 times 1 added to 2, that's going to give me a 4. And then 2 times -2 is -4 added to 5 is going to give me a 1. And then 2 times 3 added to 4 is going to give me a 2. So when I take 2 times row 2 plus row 3, my new row 3 is going to be 0, 4, 1, 2. What I want you to do right now, pause the video, take a look at those, make sure you're comfortable with how the 3-row operations work, because we're going to be using these a lot moving forward. Now time for some more terminology. One thing, what we have is what's called row-echelon and reduced row-echelon forms of a matrix. Okay, and you got to become. We're going to take a look at examples of these as well, the matrices in these forms. But this is the form. These are the forms that you're going to be working with. The first thing we have is what's called row-echelon form. And in row-echelon form, any row that has all zeros in it is going to be at the bottom of the matrix. And then for each non-zero row, so any row that is not containing all zeros, the leftmost non-zero entry is a 1, and that is called a leading 1. And what happens then for 2 successive non-zero rows, the leading 1 in the higher row is further to the left of the leading 1 in the lower row. In other words, what this means is that when I have a leading 1, all the elements below a leading 1 are going to be 0. The next thing I have is what's called reduced row-echelon form. Now, reduced row-echelon form requires you to put the matrix into row-echelon form first. So you're going to get a row-echelon form, And then, but what happens after that? Remember I said it's basically one more step. What you're going to do is that every column with a leading 1, you're going to have zeros above and below that leading 1. So remember, in row echelon form, we just had zeros below the leading 1. In reduced row echelon form, you're going to have zeros above and below the leading 1. Let's take a look at some examples, okay? The first set that I have here, this one, here, and here, those matrices are in row echelon form. So you'll notice that in this one right here, there's no row of zeros, so that doesn't come into play. Our first non-zero entry in the first row is a 1, and I've got zeros below it. In the second row, its first non-zero entry is a 1. And so this would be row echelon form. In this one right here, first row, again, no row of zeros, so that's not an issue. First row has a 1. First non-zero entry is a 1. Then I go to the second row. Its first non-zero entry is a 1, and it's further to the right than in the first row. And the same thing is true with the third row. So this would be row echelon form. Here's another one. Now you'll notice we have all zeros in this bottom row, which is where they should be in row echelon form. So our first row has a first non-zero entry is a 1. And in the second row, the first non-zero entry is also a 1, and that 1 is further to the right than the one above it, than in the first row. So that is row echelon form. Now in reduced row echelon form, what happens, again, is that the elements, when you have a leading 1, you're going to have zeros above and below that leading 1. So in this first one that we have, you'll notice that it's in row echelon form, but now we don't have, in this case, where we have a leading 1 here, we have a 0 above it. So that's what puts this into reduced row echelon form. It doesn't matter that that 2 is still there. That 2 does not have a leading 1 associated with it. In this second one right there, you'll notice this one is real nice, and you're going to see this quite a bit when you use reduced row echelon form, that you'll have a 1, zeros below. In the second row, you have a leading 1, 0 above and below. And in the third row, you have a leading 1, zeros above. And then you have the 2, 4, negative 4, and 3. And then in this third example, again, this is an example of a matrix in reduced row echelon form. We have a row of zeros. So that's on the bottom. First non-zero entry is a 1 and zeros below it. In the second row, we have its first non-zero entry is a 1, and we have zeros above and below it, and that's it for the leading 1s. And again, so we're still going to have the 3 and negative 2 there. That's not going to change because we don't have a leading 1 associated with it. The nice thing about reduced row echelon form, especially if you have one solution, is when you go and translate it back into a system of equations. Let's look at this second example here. If I translate that back into a system of equations, what I get, this first equation would tell me that x is equal to 2. The second one would say y equals negative 4. And the third one says z equals 3. So that's what's nice about when you have it into reduced row echelon form, you can just see the answer. Now what we're going to do is we're going to use what's called Gaussian elimination with back substitution to solve a system of equations. So the process that you're going to have here, the first thing you're going to need to do is write that system as an augmented matrix. And then number 2, we're going to have to use row operations to write the matrix in row echelon form. Once we have that done, we're going to rewrite the matrix as a system of linear equations. So we're going to translate that back into equations. And then we're going to use what's called back substitution to find that solution. So let's take a look at an example. This example is going to be a 3 equations, 3 unknown system. And we're going to use the row operations to go and rewrite it into the form that we want, into row echelon form. And then we can see what back substitution looks like. So on this example, what I'm using are the equations x plus y minus z equals 0, 2x plus y plus z equals 1, 2x minus y plus 3z equals negative 1. Now, when I write that as a system of as a matrix, my first row is going to be the coefficient on x is 1, the coefficient on y is 1, the coefficient on z is negative 1. Then I have the dotted lines and the 0. So you see 1, 1, negative 1, 0. My second row is 2, 1, 1, and then 1. And the third row is 2, negative 1, 3, negative 1. Make sure that you're comfortable with how I've gone through and translated that into that matrix. That's going to be key. Now what I'm going to do at this point is I'm going to use row operations. Now the first thing is, luckily for me, I already have a leading 1 in the first row. So I don't have to do anything to get a leading 1 there. Okay. So in this case, what I'm going to do is I'm going to start getting the zeros below that leading 1. So to do that, I'm going to take, the first thing I'm going to do is I'm going to take negative 2 times row 1, add it to row 2, put that result in row 2. Now, because I'm just doing something, I'm going to store it in row 2, row 1 and row 3 can just be copied over. And then when I take negative 2 times that 1, add it to 2, that's how I got the 0. When I take negative 2 times 1 and add it to the 1, I'm going to get negative 1. And when I take negative 2 times negative 1, add to 1, that's how I get the 3. And negative 2 times 0 added to 1, that's going to be 1. Make sure you're comfortable. Pause the video. Make sure you're comfortable on how I did those operations to get that row in red. The next thing we have to do is we want to get, once we have it in this form and you're comfortable with this, we need to get that to be a 0. So again, what I'm going to do is I'm going to take negative 2 times row 1 and this time add it to row 3 and store the result in row 3. So my first row and my second row just stay the same. And now what I'm going to do is take negative 2 times 1, add it to 2. That's where I get that 0. Negative 2 times 1 is negative 2. Add it to negative 1. That's what gives me the negative 3. And negative 2 times negative 1 is positive 2, added to 3, that gives me the 5. And negative 2 times 0 added to negative 1 is negative 1. So our new third row is 0, negative 3, 5, negative 1. Now I have everything all set up. Now I want to go through and my first non-zero entry in my second row needs to be a positive 1. It needs to be a leading 1. Right now it's negative 1. So what I'm going to do is I'm going to multiply row 2 by negative 1, store it back in row 2. So again, row 1 and row 3 will stay the same. And so when I multiply row 2 by negative 1, 0 times negative 1 is 0. Negative 1 times negative 1 is 1. 3 times negative 1 is negative 3. And 1 times negative 1 is going to be negative 1. So now I have a leading 1 here. I now need to get a 0 here. So what I'm going to do is I'm going to take 3 times row 1, or row 2, sorry, 3 times row 2, and add it to row 3 and store it in row 3. So again, row 1 stays the same. Row 2 is staying the same. So when I take 3 times row 2 and add it to row 1, 3 times 0 added to 0, that's what gives me the 0 here. 3 times 1 added to negative 3, that gives me the 0. Then 3 times negative 3 is negative 9, added to 5 is negative 4. And 3 times negative 1 is negative 3, added to negative 1, I get negative 4. So we're almost done. We're almost in row echelon form. The only problem that we have right now is that this element right here, the first non-zero element in row 3, is not a 0, or is not a 1. So what I need to do is I'm going to multiply row 3 by negative 1/4. And so row 1 and row 2 stay the same. And what I get is when I multiply row 3 by negative 1/4, that gives me 0, 0. Negative 1/4 times negative 4 is 1, 1. And now we can go through and solve the system. And this is where we use what's called back substitution. When I translate that back into equations, I have x plus y minus z equals 0. Not surprising, that first equation is is the first row still is the same first equation. We haven't done anything to it. Our second row, though, tells me that y minus 3z equals negative 1. And more importantly, the third row tells me, the third equation here tells me that z equals 1. So since z equals 1, I have that. I know that y minus 3 times 1 equals negative 1. So y minus 3 equals negative 1. So from that, I get y equals 2. And since we know z and y, I know x plus 2 minus 1 equals 0. So x plus 1 equals 0. So I know x equals negative 1. So my solution here to this is the ordered triple, negative 1, 2, 1. That would be the solution to that system. As before, please pause the video. Make sure that you're comfortable with everything we did here, that you're comfortable with all the row operations that I did to get it into row echelon form, and then how we translated that back into equations and then used what's called the back substitution to go through and find y and x. So pause the video, make sure you're comfortable with that, and when you are, let's move on. The next thing we have is what's called Gauss-Jordan Elimination. Now, the Gaussian elimination, that's what you're going to be doing before break. Gauss-Jordan Elimination is what I'm going to ask you to do after break. Gauss-Jordan Elimination, what we have to do is write that system as an augmented matrix, just like we did before. And then we're going to use the row operations to rewrite the matrix in reduced row echelon form. And then we're going to translate that system of equations, that matrix back into a system of equations. And when we do that, that should generally be our solution. So let's take a look at an example. What we have in this one, in this example, we have the three equations are x plus y minus z equals negative 2. I have 3x plus y minus z equals negative 4. I have 2x minus 2y plus 3z equals 3. So again, translating that into an augmented matrix, the dotted line there represents our equal sign. So I have 1x, 1y, negative 1z, so it's 1, 1, negative 1, and then equals negative 2. I have 3x, 1y, negative 1z equals negative 4. And then 2x minus 2y plus 3z equals 3. Now, the next thing I'm going to do, you're going to see we can go through, on the previous example, we just did one row operation per arrow, if you will. So sometimes you can go through and you can go through and do two. So what I'm going to do here, you'll see here on this one, I have one set of row operations in the first above the arrow, one set below. So in the first one, I'm going to take negative 3 times row 1, add it to row 2, store that in row 2. And I'm going to then take negative 2 times row 1, add it to row 3, and store it in row 3. So the upshot of this is the only row that's going to stay the same is row 1. So that's why I rewrote it right there. And so we do the first operation. That's what you see in red. When I take negative 3 times 1, add it to 3, that gives me the 0. Negative 3 times 1 added to 1 gives me the negative 2. Negative 3 times negative 1 is 3. Added to negative 1 gives me a positive 2. And negative 3 times negative 2 is 6. Added to negative 4, I get 2. So now that's our second row. So the first row stay the same. This is our new second row. Our new third row is going to be what happens when I take negative 2 times row 1, add it to row 3, put that in row 3. So negative 2 times 1 added to 2 gives me 0. Negative 2 times 1 added to negative 2 gives me negative 4. Negative 2 times 1 added to 3 gives me 5. And negative 2 times negative 2 is 4. Added to 3 gives me 7. So this is my new second row. Now the next thing we have is, again, we want, in terms of working with this, we want to go through and put, when we want to go through and put in reduced row echelon form, the first thing we need to do is get row echelon form. So we have a leading 1, we need this first non-zero entry to be a leading 1. So I'm going to multiply row 2 by negative 1/2, stored in row 2. So row 1 and row 3 stay the same. And when I take negative 1/2 times row 2, I'll get 0, 1, negative 1, negative 1. The next thing, and now what I want to do, I have a 1 there. I need to get a 0 in that spot. So that's where I'm going to take 4 times row 2, add it to row 3, and store it in row 3. So row 1 and row 2 stay the same. 4 times 0 added to 0 is 0. 4 times 1 is 4. Added to negative 4 is 0. 4 times negative 1 is negative 4. Added to 5, that's 1. And 4 times negative 1 is negative 4. Added to 7 is 3. So now, I got kind of lucky because by just doing that now in my third row, I do have a leading 1. So I don't have to go through and do anything I don't have to multiply my third row by a constant to get a leading 1. It's already set. So now what I want to do, remember, to get it into reduced row echelon form, which is what Gauss-Jordan elimination does, we want to get zeros above all the leading 1s as well. So I have a leading 1 here. I need to make this entry, the second row third column and first row third column. I need both of those to be 0. So what I'm going to do to do that, that's a 1, and these are both negative 1. So I'm just going to add row 3 to both row 2 and row 1. So the first thing I'll do is row 3 plus row 1 stored in row 1, and row 3 plus row 2 stored in row 2. So you'll notice in black I have row 3. I wrote that out first because that's the row that's staying the same. It's not changing. And so when I take row 3 and add it to row 1, well, I take 0 plus 1 is 1, so that's all set. 0 plus 1 is 1, so that's the same. 1 plus negative 1 gives me the 0, and 3 plus negative 2 gives me a 1. So that's what you see in red. It's what happens when I take row 3 added to row 1. When I take row 3 and add it to row 2, you'll see that's in blue. The 0 here plus 0 gives me the 0. 0 plus 1 is 1. 1 plus negative 1 makes that 0. And 3 plus negative 1 gives me a 2. The last thing I need to do is I still have a leading 1 there. I need to get a 0 on this one. And so what I'm going to do is take negative 1 times row 2, add it to row 1, and store that result in row 1. So in this situation right now, row 3 is not being touched. Row 2 stays the same as well. And all I'm going to do is take negative 1 times row 2, add it to row 1. So 0 times negative 1, add to 1 is 1. Negative 1 times negative 1, add to 1 is 0. 0 times negative 1, added to 0 will still be 0. And 2 times negative 1 is negative 2. Added to 1 gives me negative 1. And so now we have this into reduced row echelon form. And what I can do now is just read across. This tells me x equals negative 1, y equals 2, and z equals 3. And so my solution on this one is the ordered triple negative 1, 2, 3. That would be the final solution on that one. Again, I've gone through this pretty quick, but I want you to pause the video, make sure that you're comfortable with each step that I did in terms of putting this matrix into reduced row echelon form. And then once you are, we can move forward. The last thing we have to look at is what it means to be inconsistent or dependent systems. Now, everything we've looked at so far has been an independent system. And you can determine whether it's independent, dependent, or inconsistent based on the matrix when you put it into row echelon form or reduced row echelon form. When you have a leading one, the first thing you have to keep in mind is this really works when you have, when the coefficient matrix would be a square matrix. So if you have the number of variables is equal to the number of equations, okay? As long as that happens, then you're okay. In this situation right here, we have 3 equations, 3 unknowns. When each row has a leading 1, or when we put it into, this is row echelon or reduced row echelon form, these ones right here, we can go through and write a system, and then we're able to solve that system. In this case, we would have z equals 3, and we could use back substitution to solve it. In this case, I already know the solution. X is 2, y is 1, z is -4. When we have something that's inconsistent, what's going to happen is that when we write it in row echelon form or reduced row echelon form, what you're going to end up with is in the coefficient matrix, a row of zeros, but in the solution matrix portion, you're going to have something other than 0. Okay, so in this case right here, we got a 3. So in this case, I'd have 0x plus 0y plus 0z equals 3. That's impossible. There's no way that I can have 0 equal to 3, or over here 0 equal to -1. This is in reduced row echelon form. So in this situation, both of these situations right there, those aren't possible. So that would be an inconsistent. That would be systems that were inconsistent. Systems that are dependent have multiple solutions. And multiple solutions happen when you're dealing with the 3 equations, 3 unknowns, 4 equations, 4 unknowns, 2 equations, 2 unknowns, when you end up with a row of zeros. So in both of these systems, this one is in row echelon form, this is reduced row echelon form. You have a row of zeros, so you would end up with a system of equations here which is dependent. It would have multiple solutions. Okay, so when you see a row of zeros like this, when you have the number of equations is equal to the number of variables, you know that you have a dependent system which is going to have multiple solutions. If you have fewer equations than variables, then you know you're at least dealing with a dependent, or you're dealing with a dependent or inconsistent system. There's no way it can be independent. Okay, if you have fewer equations than variables, then there's no way it can have one solution. It's either going to have no solutions or many. And if you have more equations than variables, so if like you have 3 variables but 4 equations, then obviously what's going to end up happening, you're going to have a row of zeros down there. So in that situation, you could still end up with an independent, inconsistent, or dependent. It's just got to be what happens in terms of how many rows of zeros. If you have, if the number of non-zero rows is less than the number of variables, then it's going to be either inconsistent or dependent. So with that, that covers what we need to know on 8.3. We will go through in class. I'll do an example of one involving Gaussian elimination. I'll do that before break, and then when we come back, we'll review some of the elementary row operations, and we'll do Gauss-Jordan elimination to solve the system as well. So you're going to see both of those. But remember, Gaussian elimination is going to be what we're going to focus on before break. Gauss-Jordan elimination is what we're going to deal with after break. So with that, I hope that you have had, hope everything is going well, and I will see you hopefully in our next class.